Thank you.
All right. Yeah, thank you for coming to this last talk of an eventful day. So as one of the organizers, I can say that this has been a great conference. And I definitely thank the other organizers, especially the local organizers who have worked so hard, and all the speakers. I really enjoyed both the physics and the reminiscences. And some of them were a bit unexpected, something I didn't know. For example, from the talk by David Kaplan earlier today, so he talked about meeting David Gross in the spring of 1981 as a prospective graduate student. And I met David a year later in the spring of 1982. And remember, also had a very memorable discussion, which actually involved some stuff from David's talk, which was zero modes trapped on kinks. I was an MIT undergraduate and was working on the stuff that was hot at the time, this Jakiv-Rebbe stuff, and that led to my very first paper eventually with Jakiv Kerman and Gordon Semenov. Yeah, unfortunately, both Roman Jakiv and Arthur Kerman are no longer with us, so, but I'm very grateful to them for the initial research experience. But the outcome of my meeting with David was different because I actually did accept the Princeton offer. And then when I came to Princeton, I was still in the pre-revolutionary string era, pre-string revolution era. And the first projects I worked on were on hadronic physics, on the SCAR model. And now I'm actually very happy that it gave me some pre-string exposure to physics. Okay, so let me start. So we heard a lot of my introductory stuff has been, of course, scoped by many other speakers, and I'm much less qualified to talk about the early days of QCD because I wasn't in the field then, but we're here to celebrate the gift given to us 50 years ago of a really perfect quantum field theory whose Lagrangian can be put on a T-shirt, very short Lagrangian. It's a UV complete theory. It's asymptotically free. It is the part of the standard model that can stand alone. It need not be embedded in a bigger unified theory. And of course, it admits a lattice definition that matches onto the asymptotic freedom well, while allowing the theory to be defined non-perturbatively at long distances. And of course, it's been honored in 2004 by the Nobel Prize for the asymptotic freedom. I'm very honored to be speaking in front of both Frank and David here. So this is from, I think, from the Nobel announcement. Okay, but of course it leaves us with a lot of work to do, and the confinement problem, which has figured practically in all the talks, why are colored quarks and gluons not observed as asymptotic states? They sort of run along at very short time scales, but then things hadronize. There are some world's experts on how this happens here. In particular, today we heard several talks. But the confinement problem, even though I think in one of the talks it was declared to be solved, but that's not apparently the opinion of the Clay Foundation. Actually, when I mentioned to people that I want to work again on the confinement problem, which was actually, when I came to Princeton, this was considered the it thing. Some people say, is it already sort of like under control? And but there is definitely no analytic derivation of confinement. There is very strong lattice evidence. So the status is unsolved, and there is still some money in it. I mean, this was one of the millennium problems, and back then it was endowed with a whopping 1 million sum, but in these 23 years, there has been some inflation. So I'm not sure if they upped it a little or not, but anyways, we're certainly not in it for the money. We want to understand QCD. Somehow it froze on me.
Tap the
Oh, tap the,
That's what they told me.
Oh, okay. Okay, so a couple years ago, we applied for the Simons confinement collaboration, or more precisely, collaboration on confinement and QCD strings. And that was a lot of work to apply for it, but to our amazement, we actually did get the funding. And this, of course, this conference is very much what we want to learn and build on. And several of our collaboration PIs are here, most notably the next speaker, David, and also Raju Venugopalan, Sergei Dubovsky. I hope I'm not missing someone. So this is, so as any group of people, we need something to inspire us. So we have this very nice image of which symbolizes confinement of three colored objects in a kind of crystal ball that was made by Grisha Tarnopolsky, one of our PIs. And a motivational quote that occurred to me recently, actually, when I saw a trailer for Oppenheimer, was when Oppenheimer says, "It's about unleashing the strong force," or something like that. Okay, another of our logos is, oops, sorry. Yeah, it's this object here. So people ask us, what are we actually going to be doing? And well, the hope is to have some this triangle, the interplay between analytical theory, computation, and actual data, phenomenology, for example, discoveries made at LHCb of new exotic states. And another slogan of ours is, since we're in LA near the movie industry, ABC. I don't know if you recognize which movie ABC comes from, but was a little bit different there. One of the words was different. I mean, this is A, always B, B, C, closing. This was from Glengarry Glen Ross, but we replaced closing by collaborating. Okay, so, but we're still in the early stages, so we're building up. And so now this is something you already heard a lot about from true experts, the Euclidean Monte Carlo, Euclidean lattice SUN theory, where you have a strict criterion for confinement, which is realized at strong coupling, just the area law for a large Wilson loop. It's easy to see in the strong coupling expansion, where you just expand e to the s and powers of s and tile the loop by elementary plaquette terms. But of course, to obtain the continuum limit, we need to go all the way from very large G to very small g, because thanks to the asymptotic freedom, as you send lattice spacing to 0, you also have to send the G in the action to 0 in an appropriate way, which is denoted here at one loop level. So this leads to, so this follows from the famous one loop QCD beta function, whose 50th anniversary we're celebrating. And one outcome of this formula, basically inverting the solution, is the so-called dimensional transmutation, namely that we have to send A naught to 0 and G naught to 0, keeping this quantity lambda QCD fixed. Here I'm just working at one loop level, so I ignored the prefactor that appears from two-loop beta function. And the bottom line is that the bound state masses and the square root of the string tension should be of order of this dimensionful quantity lambda QCD. This is, of course, indeed observed on a lattice. So as Michael Kreutz, one of the pioneers, told us yesterday, already in the 70s, there was evidence for confinement from lattice work and the emergence of dimensional transmutation. In particular, if you study the quark-antiquark potential, while at short distances it's approximately coulombic up to a log, but it pretty quickly crosses over into the linear regime, actually quite early at relatively weak coupling. So this is from a paper already quite a while ago, and I think this all is continually being sharpened. But the question is, can this asymptotic linearity be proven analytically? And at least I'm not aware that it can yet. Okay, but on a lattice we see, for example, there are these popular pictures made by Lineweber's group in Adelaide. You see the structure of the string, and as you move the probe quark-antiquark further apart, the thickness of the string does not visibly change. It's only a very slow logarithmic effect on the thickness of the string in the middle. And by now there is a lot of evidence that when you make these strings long, they're described by the Nambu-Goto area action, and this is the connection between QCD as we know it now and the original idea of string theory describing hadrons. Okay, so another thing that you heard repeatedly is the idea of large N. That improves things in the sense that even with dynamical quarks, the flux tube cannot snap in the middle, because in real world you cannot make the string very long, much longer than a femtometer, because of creation of a quark-antiquark pair. But this is suppressed by large N, so that was another milestone in non-perturbative QCD, and the introduction of the 12th coupling G squared N. That gave us a whole bunch of things to do, and as also mentioned earlier, one of the first models of non-abelian models of confinement that was solved was the 1+1 dimensional version of QCD in the large N limit, which is the 12th solution of this model. Okay, so now this is all you already heard, maybe apart from attempts at jokes that I just made. But now there is actually another kind of anniversary, and this was not so much emphasized in talks earlier. There's been a massive parallel development to real QCD, which is work on a kind of cousin of QCD. Some people say it's a distant cousin, some people say it's a close relative, but it's basically another world, a supersymmetric world of very strong coupling and nearly conformal or nearly conformal invariance. And this development has been very vigorous, and I'm sort of an ambassador from that parallel world. It started with developments in exact dualities of superstrings, and in particular, Joe Polchinski pointed out that there are these natural objects called Dirichlet branes or D-branes, which preserve half of the underlying supersymmetry of type 2 theory, and there's things on which strings can end. So their dynamics is defined by open strings that are sliding along the branes. And people pretty quickly realized that a stack of n parallel, say, Dirichlet 3 branes realizes the maximally supersymmetric SUN gauge theory in 3+1 dimensions. But then you already by then, there existed solutions describing these so-called Ramon-Ramon charged brains, which have the following very simple-looking metric. I even wrote it down. It's a warped product of the 6-dimensional transverse space, which is here, and the 3+1 dimensional space longitudinal to the brain. And the warp factor has this amazingly simple form. So this was first discovered by Mike Duff and independently by Horowitz and Strominger. And then so R is the radial distance in the 6-dimensional space transverse to the brain. So if you go to very small r, then you can drop this one. And this metric approaches, you see that in front of the d omega 5 squared, which is the metric of unit sphere, you're just left with L squared here. This L squared remains. And L squared can be made very large. Actually, L to the 4 turns out to be the 't Hooft coupling in string units in times some dimensionless. This alpha prime, which is L string squared. And the other coordinates combine into a symmetric negatively curved space, ADS5. So we get this, and this solution was already known before. So you find a solution that in the throat has this ADS5 crosses 5 structure, but then it opens up into 9+1 dimensional space, flat space. So that gives you an idea that somehow you can describe the large, in particular, the large n limit gives you sort of a heavy object which curves the space appreciably, and one can try to make comparisons between the super Yang-Mills theory living on the brains and the metric. And the early comparisons included, for example, computation of the near extremal entropy, thermodynamic properties, and that reproduced the idea that there are n squared degrees of freedom, and the factor t cubed came out, and then you can probe these objects by throwing, for example, gravitons from an external space, and that passed some checks. And eventually, so Juan Maldacena wrote a landmark paper which showed how to take the sort of conformal limit by zooming in on small r. Then you're just left with ADS5 crosses 5 and a kind of decoupled Yang-Mills theory. And so this is a kind of funny picture where you see the hyperbolic space and it's tiled with cows. Usually you see it's sort of the Escher diagram. But the cows are supposed to remind you that this is a kind of spherical cow of gauge theory, right? Because, spherical cow is sort of idealization. So n equal 4 super Yang-Mills definitely appears to be the most symmetric, the most idealized cousin of QCD. The beta function exactly cancels to all orders, and people have had a lot of fun studying this theory. You can basically start changing the coupling from very small value to very large value and see how some non-supersymmetry protected quantities change. I think we'll hear talks about it. In particular, Grisha Krachemsky will talk about it. So there has this large community has developed, which for over 25 years has been working on these things. But then one question is, what does this have to do with confinement? Because, this is a conformal field theory. There is no sort of scale emerging from it. And the question is, how can you deform it to make confinement? Yeah, before I get to that, just wanted to say that, so it's very important to work in the large 't Hooft coupling limit to get reliable gravitational description, because the supergravity approximation only emerges when 't Hooft coupling is large. So it gives you a totally new type of expansion in inverse powers of the large 't Hooft coupling, which is sort of complementary to the usual Feynman graph expansion giving powers of lambda from planar graphs. So one one question is, can you compute the QQ bar potential? And this was first done in these papers by Maldacena and by Ray and Yi. And not surprisingly, you get an exactly Coulombic potential. The only thing that depends on lambda is just the function in front, function of lambda in front. It starts out as something of order lambda, but then at strong coupling, it extrapolates to something of order root lambda. And this is basically the boundary of ADS is, corresponds to the UV, the short distance of field theory. You add probe quarks at the boundary, and then you look at the basically the action of the string connecting them. And that gives you the proper method for calculating QQ bar potential. But this gives a kind of idea for what how you can modify the theory to basically to modify the theory to make it confining. What you need is to introduce a kind of infrared wall, like this z coordinate, which is 0 at the boundary and goes to infinity in ADS space. If it's somehow ends, space ends there in some smooth way, and the string then just sort of goes there and stretches along, that gives you a linear transition to linear QQ bar potential. And I'll show you an example where this really happens and not just sort of put in by hand, but happens dynamically. Okay, so one way, so another complaint I hear is that, oh, this is only maximally supersymmetric theory, but actually already in the very earliest days, people figured out how to break supersymmetry, for example, to n equal 1, by putting these branes not in a flat space, but at the apex of some 6-dimensional cone. And one particularly, so I invested many years of my life working on the particular example of conifold, which is a rather generic sort of cone that arises in conic singularity arising in Calabi-Yau spaces. It's simply described by the equation z1 squared plus z2 squared plus z3 squared plus z4 squared equals 0. So you just solve this equation, and when you solve it, you find that the base of the cone is a particular coset space called T11 for some historical reasons. It can be described as a circle bundle over a product of two spheres, and topologically, it's not 5-sphere. It's actually a 2-sphere times 3-sphere, which helps a lot to make this, deform this theory in interesting ways. So I wrote a paper in '98 with Witten, deriving the gauge theory on these 3 branes at the tip of the conifold, and it turns out to be still a pretty standard-looking theory, the type that experts on supersymmetric gauge theory they do much more complicated things than this. It has 2 gauge groups, so there is SUN cross SUN and some bifundamental matter and some quartic superpotential. And this theory passed various checks of being dual to ADS5 cross this T11. T11, you can just say it sort of replaces the sphere. It's a more complicated Einstein space. So now, very briefly, I want to tell you how to turn this theory into a running and confining theory. You basically want to, in addition to 3 branes, you want to add some number of 5 branes wrapped over the sphere, the 2-sphere of the conifold. And then these branes introduce some other type of flux that pierces the 3-sphere and blows it up. And this is the schematic structure of the resulting space with blown up 3-sphere. But amazingly, the final metric still has a very simple structure. It's a warped product of still R3, comma 1 and the metric on this deformed conifold. So the crucial thing is this deformation. This deformation really incorporates the confining scale of the theory and incorporates dimensional transmutation. If you don't do this deformation, you still get the solution right sort of at large R, far in the UV. And this was done initially by Arkady Tseitlin and me. But that solution, which set epsilon to 0 artificially, had the naked singularity problem. So it was happy for a while, and then it underwent this sort of disastrous vanishing of the warp factor and naked singularity. So this is how the geometry tells you that you've done something wrong. You haven't done things right. And to do things right, you just introduce this very simple and deformation, which seems like the simplest thing you can do. You just put in the right-hand side, epsilon squared. This is called deformed conifold. And then everything works out actually amazingly well, and you get a confining theory. This theory has, so while in ADS space, this warp factor blows up at small r as 1 over r to the 4, here it just approaches a finite value. And the finite value of this warp factor is what gives the string attention. So the string will naturally go to this tip of this deformed conifold and retain its tension and become the confining flux tube of this theory. So that's the picture. It's a kind of, if you accept this duality, the space stays weakly curved everywhere. So there are various interesting things happening because this theory is n equal 1 supersymmetric, and in some way is very reminiscent of n equal 1 supersymmetric gluon dynamics. In particular, it exhibits R symmetry breaking from Z to M to Z2. And it does exhibit dimensional transmutation because all the global masses are discrete. They're the normal modes of this throat, and they're of order epsilon to the 2/3. But if you look more closely, actually the IR theory can be thought of as SU2M cross SUM. And the amusing thing is that there are some baryon and anti-baryon operators that acquire VEVs. So the U1 baryonic symmetry is broken, and as a result, there is a Goldstone boson a bit similar to pion and its massless scalar superpartner. So this gives you a confinement without a mass gap, actually, because of, again, similar to QCD with massless quarks. And as I mentioned, the fundamental string at the bottom of the conifold describes the chromoelectric flux tube. Okay, and then one can try to compute in this model the quark-anti-quark potential. This was actually done by an undergraduate student already many years ago. Sorry, it's a bit faint, but it has the same qualitative features as the lattice graph. Basically, it starts out as 1 over r to r modulo some logs, although logs don't go in the same place as in the real QCD, but it's still basically coulombic, and then it becomes linear, turns over and becomes linear because of the string sort of going to the bottom of the conifold. So this provides a kind of a toy model for I would say not for QCD, but for n equal 1 supersymmetric QCD. But of course, so one funny feature of this theory is that these 2-gauge groups can flow using the Novikov, Schiffman, Zakharov beta function. One can show they sort of flow in a zigzag way while staying strongly coupled. And there is a cascade of Zyberg dualities. So this is all like a little complicated. But there is there is logarithmic flow, but there is no asymptotic freedom. There is a big obstacle to getting asymptotic freedom because this duality really likes very strongly coupled series. And when the gauge theory becomes weakly coupled, you need some new methods. So that's sort of a complicated toy model, but it does give dimensional transmutation and confinement and the Goldstone bosons and things like that from a very different point of view of the dual geometry. Okay, so this is a bit of a, so I worked on it a lot about 20 years ago already, and I think the work is continuing, but then let me tell you what I've been doing. How much time do I have?
Still have about 10 minutes.
Okay. So what I've been doing more recently is to drop back to much simpler toy models. The toy models that we heard about in several talks already, namely Schwinger model and its generalizations. So to me, this is recent work, but in fact, it comes from a much more distant past than even this. But I hope you'll be amused by some of the results that I'll tell you in this. So this is something that probably is much better known to most people. So Schwinger model is actually as old as I am, 1962. It's QED in 1 + 1 dimensions, and it admits even a theta angle, which is like an asymptotic value of electric field. And the theta angle will play a big role in what I will be saying. It's exactly solvable for m = 0, which can be done in various ways. I think Frank explained one way to do it, which is to go to a 1 = 0 gauge and then look at the effective action for A0. It becomes this famous Schwinger boson of mass E/√π. In some of my slides, I switch from E to G, but different papers do not. It's basically the dimension-full electric charge. So when there is a dimensionless ratio, which is m/E, when m/E is very large, Frank explained how the spectrum of the theory is basically like 2m plus the spectrum in the Airy potential, in the linear potential. But then as you go to stronger and stronger coupling, a miracle happens, and there is only one sort of dynamical field, which is a very tightly bound state of electron-positron pair. And in this sense, it's sort of a simple model of confinement. Okay, now lattice Hamiltonian approach, that's something I've been learning also the last couple years. It also comes to us from the 70s. In particular, it's the Kogat-Susskind approach, which was then applied to this particular model by Banks, Kogat, and Susskind. This was already explained in Lenny's talk, I think. There is a term E² A/2 times sum over ln squared shifted by theta over 2π. And ln, so you have like gauge variables are living on links, and fermions are living on sites. And here, what lives on each link is just a phase. So ln is just minus I d by d phi n on each link. Then there is some mass term, which is this alternating sum. And then there is the gauged nearest neighbor coupling with the UN sandwiched in between. So the strong coupling expansion was first done in this Banks et al. Paper, but they did not spell out Gauss law constraints. In fact, there is something funny about these Gauss law constraints, and they were first spelled out by Hamer and collaborators. Essentially, in one dimension, you can just eliminate ln variables on an open segment just by solving them. And Qn is the charge due to the site. Like this is just discontinuity in the electric field, basically, given by the charge. Each two-component fermion, so it's staggered fermion, meaning that the upper component lives on even sites and lower component on the odd sites. But then there is a necessity of defining charge differently on even and odd sites. It's very important because unless you subtract this -1 on the odd sites, you will not get a sensible theory at all. Because of this, it's sort of lives at half filling, and there is interesting dynamics. If you say that Qn everywhere is chi-n dagger chi-n, then you get nonsense. And I mean, this was implicit in Banks et al., then you notice the following thing, so what is the remnant of chiral symmetry in this model? Since each fermion lives on two neighboring sites, The usual translation is really a translation by two sides. And so what is translation by one side? That's supposed to be a remnant of the chiral symmetry. But this is already broken by how you define the charges. So something funny is happening. So it turns out that you can take care of this by shifting what you mean by the lattice mass. You can compensate for the staggering of the charge by shifting the lattice mass. And this is an improvement term which is actually linear in A. And so this was noticed by my collaborators and me in this paper about a year ago. And then at m equals 0, this point is protected by a kind of, it's not quite symmetry, but it's something like symmetry, because you shift by one lattice unit, but also have to shift theta by pi. But then if you implement this shift, the strong coupling expansion completely changes, because before people were taking this mass parameter to be 0, but now you actually have to change it to -1/4. And that actually does something miraculously good to the strong coupling expansion. If you read all these old papers, they try to do it, and then they're like, oh, this Pade is awful. This doesn't make much sense. Once you work at this shifted point, like you use all the old formula, but just work at this -1/4 point, this is the dimensionless energy gap. Pade extrapolating with just 3 terms gives you the mass of the Schwinger boson to 0.1%. I mean, I'm not saying that this is, it's not true for all quantities, like the VEV only came out to 1%, but it's clearly something good happened, and a dramatic improvement of strong coupling expansion, and also gives very strong improvement in just exact diagonalizations on finite lattice, which we did. Okay, so this kind of helps you get the nearly massless fermions under control. Well, you can just say.
Use approximate methods. If this model is exactly solvable.
Well, no, but it's not exactly solvable even at small mass. Then you can. No, I mean, people keep trying to do, say, the Euclidean Monte Carlo for this model. And actually, the small mass deformation is very tricky, like the low mass region. You can also do it on light cone using the LCQ, as Stan Brodsky, I think Brodsky and Pauli did in the 80s. But then there are, all these. So the massive Schwinger model is not exactly solvable. But the massless limit gives you a benchmark for comparison. So let me finally amuse you by something a little bit new, not just some numerical improvement, which is the good old two-flavor Schwinger model, which there was a classic paper by Coleman in 1976 called More on the Massive Schwinger Model. And that did a lot of beautiful stuff, but left some loose ends. And in fact, he lists a few questions at the end of this paper. In particular, what happens at theta equal pi? And it turns out that at theta equal pi, there is a possibility of breaking of charge conjugation symmetry. In fact, even in the one-flavor Schwinger model, if you go to theta equal pi, which is same as theta equals 0 at negative mass, there is a critical mass beyond which there is breaking of charge conjugation symmetry. But then it gets more interesting in this two-flavor model, because then there is a two-parameter region with the two masses. And this is closely related to Michael Kreutz's talk. In fact, he showed a diagram, a phase diagram, which is, when I saw it, I was very surprised, because this is just the same as the phase diagram that appeared in our paper in May. His one was rotated by 90 degrees, but that's just the reason, because if you plot it at theta equals 0, that's like working with one positive mass and one negative mass. So you just rotate it like this. And this is what, based on various evidence, we think what happens. So at very large mass, you have this Z2 transition that was already observed in the one flavor model. And this happens at this critical mass, which turns out to be extremely close to G/3. And then you have a corresponding thing here. So the boundaries of this region are two-dimensional CFTs in the Ising universality class. These two lines merge at the origin to the exactly solvable C=1 point, which is a well-known solution from Coleman paper. It's the self-dual scalar, or SU2 level 1 WZW model, which has SU2 cross SU2 symmetry. But then in this shaded region, the charge conjugation symmetry is spontaneously broken. And as I mentioned, there is already there is analogy to the 4D QCD from Kreutz's talk yesterday and from the original work of Dashen. Now, very quickly, you can see this picture from both the continuum methods and from the lattice methods. So in the continuum methods, this is literally what was in Coleman's paper. You bosonize the two fermions, you get two scalar fields, phi1 and phi2. You form the plus and minus combinations. The plus field gets massive in a similar way to how it happens in the one flavor Schwinger model. And all the interesting stuff is in the minus field. The minus field is just a periodic field. So for generic theta angle, like theta equals 0 or anything not equal to pi, you get this operator. You basically get the sine-Gordon model at beta equal to square root of 2 pi. And then you can show, and this was shown already by Coleman, that the mass gap will go like m to the 2/3 power, just by power counting, essentially. But now this vanishes at theta equal pi. So could this theory be actually gapless? So this is the miracle at theta equal pi. And Howard Georgi wrote a couple of interesting papers sort of raising this question. But definitely Coleman left this as not completely clear what happens at theta equal pi. What do we think happens? Well, numerically, it's very close to 0, but I think the gap is actually non-exponentially small. And this follows, so a kind of dimensional transmutation occurs in this model. And so if you follow through what Coleman did, he gets this beta equals square root of 8 pi sine-Gordon model. And then this operator is just marginal. So then you have to, this is what is now known as the BKT flow, or the Berezinski-Kostelis-Thouless flow in the sine-Gordon model. This was studied in various papers. I think Kosterlitz wrote a paper, but then in more detail there was Amit, Goldschmidt, and Greenstein. So you actually have to include the flow of two couplings, the coefficient of the phi squared term and the coefficient of this nearly marginal cosine. And this picture maybe you've seen in various textbooks. It's a two-parameter flow. For us, we know that the flow is SU2 symmetric. So it picks out the one particular straight trajectory that emanates out of this free theory, free self-dual scalar. And the beta function is just like the QCD one-loop beta function. It's asymptotically free, and the effective parameter is m squared over g squared. So you get dimensional transmutation, and the gap is expected to be e to the minus a constant times g squared over m squared, and even this constant is computable. So that's the dimensional transmutation and the two-flavor Schwinger model at theta equal pi and small mass. And we did the numerical work on this, And here, because it's in a very low mass region, this mass shift makes things much more precise, and it's important. I should stress that in the two-flavor model, this is a genuine symmetry. You don't need to shift theta by pi, because you just see that with nf equal 2, the shift by one lattice site at m lattice taken to be minus g squared a over 4, the Hamiltonian is symmetric, and that's extremely helpful. It protects the massless point. Here, then it's very hard to compute exponentially small gaps, but we use the technique of computing entanglement entropy. And these are the lines that actually do indicate this phase diagram. You see how close by these two c equal 1/2 lines are. They really merge into this merge here. And we do see evidence of c being 1/2 along these lines. So, and we see this exponentially long correlation length, basically. Okay, so now I just need a couple of minutes. So this is the very tricky part. What happens at theta equal pi? What if you drop back to theta equals 0? Even there, the small mass region is numerically tricky. So here you find the sign Gordon with beta equal to square root of 2 pi, and the mass gap should turn on as m to the 2/3. And what Coleman, you read his beautiful paper, he predicted an SU2 triplet with this. There are only 4 particles with this mass scale. The lowest is pions, the triplet, and then the next one is a sigma, a singlet. But the sigma is a bound state. It's not a resonance like in QCD. And the ratio of masses is square root of 3. That follows from the Sine-Gordon integrable description. But I think before people did not actually see this root 3. Just a couple of months ago, Etsuko Ito and Matsumoto and Tanizaki wrote a very careful paper where they used the MRG, tensor network methods, and used the mass shift that we derived, and they give this mass shift, the ratio comes out really root 3. So this is a very, apparently somehow they're not convinced that this is a rigorous ratio, but they do obtain it. So there is interesting work to do even at theta equals 0 here. The small mass regime is very interesting. So let me just end. So I showed you two models of dimensional transmutation and confinement. One very complicated one using string theory and 10-dimensional metrics and so on, and describing some very complicated RG flow with n equal 1 supersymmetry, which then gives computable spectrum and dimensional transmutation. And then the good old two-flavor Schwinger model for theta equal pi and low mass. And I think the striking feature is these exponentially small gaps. I'm not sure we fully understand the structure of the spectrum. I think it's an interesting challenge to calculate numerically whether one can really get the spectrum at theta equal pi in small mass. And the lattice Hamiltonian approach with tensor network methods gives really precision results for many 1+1 dimensional models. So it looks worth revisiting in 2+1 and 3+1. And of course, it has connection with real experiments like quantum simulation. And in particular, Peter Zoller built a multi-atom chain which simulates the one-flavor Schwinger model. So I think there is a lot of new techniques. I think these models have a new life, and I'll end here. Thank you.
Thank you very much for this beautiful talk. I think we have time for one short question. Okay.
Just maybe too simple or too complicated, but I want to ask, okay, you're interested in the domain where E divided by M is very large parameter, or on the other hand,
Strongly
M
coupled,
divided by E, yeah, a strong coupling is very small. So usually, if we have in a theory a very large or a very small parameter, some kind of expansion might be applicable, right? Usually, it's not the theorem, but instead of maybe, is there any, say, no, it should not, I don't know, some kind of expansion. Can it be found, or you have really to do it on a computer?
No, I think I did show the analytic approach in terms of the Sine-Gordon model, right? The continuum, so bosonization gives Sine-Gordon model which are under control in this regime. So there are two regimes. One is generic theta, in particular theta equals 0, and then you get the effective Lagrangian, which I'll show you. It's this one, right? It has this cosine of root 2 pi phi minus. There is one light field, phi minus, and you got to solve this model. And this model is basically solvable. And that's how you see this isotriplet of pions and the bound state of them, the sigma. But then, so this was in Coleman's paper. And but then the theta equal pi, something very special happens. And he has a section on theta equal pi that this breaks down. Then instead, you suddenly get this cosine square root of 8 pi. That's a marginal operator. But then again, you can use the RG. You can use RG. It's a lot like QCD. So you see that this coefficient here is m squared, so it's small. You can use perturbative beta functions, namely these Kosterlitz beta functions. And these are the flows you get. And this motivates, so of course this doesn't let you penetrate all the way to the infrared, right? Because like this theory has its own confinement problem, right? All you can see is that this trajectory starts from weak coupling. This is this trajectory, it's the straight one. It goes off like this. It starts out very near weak coupling and it goes off to strong coupling. But it lets you estimate lambda QCD, right? And this lambda QCD is exponentially small. That's basically the logic from the RG. But then the lattice computation, that can buy you a lot more. I don't know, I would not be surprised if one can do a lot better than this. But the fact that this very simple model has dimensional transmutation, I think, was not appreciated before. So maybe it's actually a better model for QCD than, say, the well-appreciated one-flavor Schwinger model.
Thank you very much. I suggest that we thank Igor again.